Okay, so here we are on the second video of optimization problems with exponential functions. So the first video was more straightforward. Now these examples get quite a bit more difficult. So hopefully you can follow. I'll try to take my time, but please be responsible in making notes or making asterisks where you don't understand something so I can address these issues in class with you, okay? So let's take a look at this function. Okay, so we don't have any idea really what this looks like. I will show you in GeoGebra when we're done what it does look like. But it is a quotient of two exponential functions, specifically with e to the x. As the exponential part. So prove that f of x is always increasing. So we're going to do that by showing that the derivative is always positive. Okay, then show that f of x has two horizontal asymptotes and determine their equations. And we are going to do that with looking at the limits of the end behavior. So we're using calculus concepts in both of these cases to answer these questions. Now, if you did just graph it, obviously you could see that it's true, but we want to connect our understanding with our calculus knowledge. So for part A, like I said, to prove that f of x is always increasing, we're going to find the derivative and show that it's always positive. So we're going to look at this as a quotient, so we're going to use the quotient rule. So we take the bottom, and we multiply it by the derivative of the top. So the top is 2, so that goes to 0. And then 3 e to the x. Remember, the derivative of e to the x is just e to the x, so the derivative of this is just 3 e to the x, okay? Minus the top times the derivative of the bottom, so that was just 2 e to the x, all over the bottom squared. Okay, so now we want to simplify this. So notice that we can factor out an e to the x from these multiples. So we're going to take out an e to the x. Okay, and then we're left with 9. 3 times 3 is 9. Plus 6 e to the x. Minus 4, 2 times 2. Minus 6 e to the x. Okay, all over the bottom squared. I'm just going to leave that. And then, so if we simplify this, we get 5 e to the x all over 3 plus 2 e to the x squared. Okay, so now we can conclude, since 5 e to the x is always positive, right? Because e to the x is an exponential function that looks like this. So it's always increasing, and then it's just being multiplied by 5. And then anything squared is always greater than or equal to 0. So therefore, the derivative is always greater than 0. So therefore, f is always increasing. Okay, so that is part A. Okay, let's go ahead to part B. Okay, so we're going to use limits. So we'll use different colors for the two limits. So we're going to show the two horizontal asymptotes. So one is as x approaches positive infinity, and the other one will be for approaching negative infinity. So the limit as x approaches infinity of 2 plus 3 e to the x over 3 plus 2 e to the x. So what is happening here? Well, this is getting extreme. Okay, this 2 and this 3 kind of drop off. They don't really matter. Like as x approaches infinity, this plus 2 and this plus 3 are negligible. What matters is the ratio here. So e to the x and this e to the x are going to get huge at the exact same ratio because this is just a 1-to-1 ratio. So as x goes to infinity, the whole function will keep this 3-to-2 ratio. Okay, so that is the horizontal asymptote as x gets extremely large to the right, so to positive infinity. But what happens to this function at negative infinity? Okay, so think about it. So what's going to happen here, we're going to put our result here, but let's think about this. Let's think about this. So we're going to get 3e to some really, really negative x over 2e to some really, really negative x, okay? Because these additions here don't really matter, okay? So negative x's mean that you flip the base. So this would go to the top and this would come to the bottom due to the nature of negative exponents. So as you get really, really negative, this limit is actually 2/3, okay? Not because this 2 and this 3, they don't matter, like they are negligible. It's because this 2 comes to the top and this 3 goes to the bottom because we have negative exponents. So the equation of that, horizontal asymptote is y equals 2/3. So if we actually go to GeoGebra, I have this graph for you so you can see what it looks like. So there it is. This is the function. So here we have the horizontal asymptote of 3/2 or 1.5. And here, as we go to negative infinity, you can see it's 2/3. All right. And actually, you can also see that it's always increasing. Okay, let's go to example 5. So for example 5, we'll take a read at it. One side of a rectangle lies on the x-axis. The opposite side has vertices which lie on the graph of this funky function. For what value of x is the area of the rectangle a maximum? So to be able to do this, we need to draw a diagram, okay? It's really hard to wrap our head around what's going on until we actually draw a diagram. So let's actually graph f at x just so we can visualize what's going on. So we're going to use our chapter 4 knowledge to do that. So let's take the derivative of this. So the derivative is, itself times the derivative of the exponent. Okay, so we can see that x equals 0 is a critical point, okay? Because if we sub 0 in for x, we get a derivative of 0. Okay, I guess I should say since f prime at 0 equals 0. Okay, so let's determine the nature of that critical point. So if you look before, so if you have x is less than 0, okay, you get that the derivative is, what is it? It's positive. Yes, you get a positive derivative. And if x is greater than 0, then you get a negative derivative. So we have 0, comma, okay, if you put it into the function, you get 1, e to the negative, e to the 0 is 1. So therefore 0, 1 is a max. Okay. So what does that look like? Okay, we also have on this function that as x approaches infinity, what's happening? Okay, y is approaching 0. Okay, if you look at this function, e to a really, really, really large number squared, then become negative, okay? Because it's not, you have to square the number first. So you're getting e to some really, really negative number that's approaching 0, whether x is positive or negative. Okay, so what this looks like, you could analyze it further if you needed to, but I think it's pretty clear, is, let me some space here. You have it approaching 0, and then we know it's increasing up to a max and decreasing back down to its horizontal asymptote. That is a terrible picture. Okay, something like that. So when you draw this rectangle in here, it says it has one side lies on the x-axis, so that's down here. And then the other ones lie up here. So but the thing that we don't know is where it touches this guy. okay? We don't know where it touches this guy, that's the problem. So we want the area of this rectangle to be a maximum. So therefore we need an area function in terms of x, and then we need to maximize that area function. So what is the area of this function? Well, it's length times width, okay? So what is this length? Well, this is x over here, and then this is an x over here. So the length of this rectangle is 2x, okay? So its length is 2x. Now, what about its width? Well, it touches however high this function is. So its width is actually equal to the function. Okay, so its width is however high this is, which is e to the negative x squared. So this is actually the area of a rectangle that would work here. And that allows us to kind of play around with, is it that has the biggest area? Or would it be, more skinny like this? Would this have the biggest area? So this equation allows us to entertain all of these different possibilities because it's in terms of the variable x. So now to maximize this function, we take the derivative of it and set it equal to 0. Okay, so it's a product. So we take 2x times the derivative of this, which is minus 2x e to the negative x squared. And then we add the derivative of 2x is 2, e to the negative x squared. So we can factor out a 2 and an e to the negative x squared. And we're left with minus 2x squared plus 1. Okay, so we want to set a prime equal to 0 and solve. So this part can never equal 0, so we just need to care about this part, okay, since this part can never equal 0. So that gives us 2x squared equals 1. So x equals plus or minus root 1/2. Okay, which can be written as plus or minus 1 over root 2. So for what values of x is the area a maximum? Well, there you have it. It's these two values of x. Okay. So if you want to take a look at what that function looked like, I did graph it here. So there, you can see what it actually looked like, so which is a much better drawing than what I did. But hopefully you can see that doing this diagram does help you visualize the problem. All right, our last example involves a logistic function, and this is mostly just going to be limit work here, like finding different limits. So hopefully you guys find it enjoyable. I kind of find it a little fun, but you know me, I'm a little wonky sometimes. Okay, this is a logistic function. So it allows a model for growth to be adjusted for the fact that growth is not infinite. For example, population growth can be limited by space, food, predators, and so on. So if you remember at the very end of advanced functions, we talked about this. So it's the kind of graph that will have some kind of upper limit like this. So it usually looks like kind of like an S, like it grows, but then hits maximum like that. Okay, so we're going to use limits though to prove the different portions of this function. So determine the limit as x goes to infinity and negative infinity. What is it? So the limit as x goes to infinity of c. So before I write this all out, notice that c is a constant, a and b are constants. So the only part that matters for the limit is this little exponential part. So we're going to take a look at what happens. So instead of writing that, I'll just say as x approaches infinity, what is going on with this a e to the negative bx situation? Because that's all that really matters. So to understand this a bit better, you can write it as 1 over a e to the bx, okay, with a positive exponent. Actually, you can put, I think the a is on top of this. Only the e is negative, okay? But as x gets extremely large, you'll get a number over some humongous number. So this fraction is going to approach 0. So therefore, the limit of this whole thing Okay, so this part's going to go to 0. So you get c over 1, which is just c. So that means that this, the equation of this upper asymptote here is just y equals c, because as the function gets closer to positive infinity, the entire logistic function approaches c. So what happens as x goes to negative infinity? Well, then we have this a e to the negative bx, which would become ae to the bx, because now our x is negative, and so that approaches infinity, right? Because this is getting hugely, hugely large. So our limit as x approaches negative infinity of c over 1 plus a e to the negative bx. Well, if this is approaching infinity, then you're getting c over some hugely, huge number. So the whole thing is going to 0. And that makes sense for the logistic function to be approaching 0 that way. Okay, I'm changing colors for part B. So evaluate f at 0. So f at 0 is going to be equal to c over 1 plus a times e to the 0, right? If you put 0 in there. So remember, anything to the power 0 is 1. So this is just c over 1 plus a times 1. So it's just c over 1 plus a. So that's what you get. That will be your y-intercept. Okay, show that the derivative is positive for all values of x. And then part C is prove that there are no extreme values. Which you can also say prove that the derivative will never equal 0. Okay, same thing. So the derivative of this, then, we take the bottom, which is 1 plus a e to the negative bx, times the derivative of the top, which is 0, because c is not a variable, it's a constant. So this part will all go away, but I just wanted to show you. And then we take the top times the derivative of the bottom. Okay, so the 1 doesn't matter, but our e negative bx. So remember, only e is a number. Only x is a variable. The rest are actually all numbers. So the coefficient there stays. And then the derivative of e to anything is e to anything derivative of anything. So e to anything to minus bx times the derivative of that anything, that blah, which is negative b. Okay, so this section is that derivative. Okay, all over the bottom squared. Okay, so what's happening here? So this all goes away. So a negative times negative. So actually on the top here we get a, b, c times e to the negative bx all over this junk squared. So as you can see here, the denominator is always positive, okay, because it's squared. And since we know from the original thing that a, b, and c are all always positive constants, that's what they were defined that way. So that means that, and this part is always going to be positive, so therefore the derivative is always positive for all x. Doesn't matter what you put in there, this will always be positive. Okay, finally, part D. Prove there's no critical points. So if you set this derivative equal to 0, basically that's the same thing as just setting the numerator equal to 0 and trying to solve, because if you cross multiply, that goes away. Okay, there's no solution to this. Okay, you can divide out a, b, c, so then you get e to the negative bx equals 0. There is no solution to this because this is an exponential function, so it has 0 as its asymptote. So this does not exist, therefore no critical points. Okay, I know that there's some kind of difficult concepts in here. You're combining, some graphing to help you understand things with some derivatives, which are a bit challenging, some limit work. So this really does require you to be all in with your calculus knowledge, but it's a great way for you to kind of see what you understand and to really expand your understanding when you hit those roadblocks. So thanks for watching, guys, and I hope you learned lots.